Welcome, guys, once again to our session for Grade 10 Physical Sciences. Today's session is based on representing the chemical change. Hopefully, we have a very interesting session once more, Grade 10 learners. My name is Temba Ngube. This is just a build-up to, it's a follow-up on the last section that we did, which was based on physical as well as chemical change. We managed to show differences and similarities between those two types of change as far as how matter behaves under different conditions. Right, for now, let's go straight into the overview of today's session, just to get a picture as to what is it that we seek to achieve by the end of today's session. Right, let's get right on to it, guys. Okay. Right, as you can see from the from the overview there, our focus is chemical change. Remember, when we talk about chemical change, we're talking about new substances being formed. When new substances are being formed, we know there are new bonds that are formed. So if we form new substances, it means atoms of elements or molecules are broken first. Then those which are broken are called the reactants. Okay, the reactants are those that are broken to form new substances, which we call the products. Right, so when that happens, chemical reactions take place. However, it's very important for us to understand that the atoms and elements as well as ions in terms of the bonds of the elements or the substances that take part in a chemical change are the ones that are involved in the chemical change, right? So we talk about the law of constant composition, right? What we're saying as far as the law of constant composition, just in passing, is that if you have particular substances as reactants, it certainly means that even the products must consist of the very same type of atoms. If we start with the sodium and the hydrogen on the left, it means even in the products must contain the same elements or atoms or ions. However, the combinations may differ because, remember, we said that in this typical chemical change, what's going to happen is that we're going to have new substances that are formed. And when new substances are formed, it means new bonds are also forged between these reacting substances. So the law of constant composition suggests that the reactants, the atoms of reactants must also be, the atoms of reactants are the ones that are transformed into products. In other words, if we have a particular substance as part of the reactants, it must also be part of the products, right? Even though the combinations may differ. So we represent these chemical changes using chemical equations, whereby we say the reactants, let's say A plus B, they react to form, let's say, a new substance AB. Even if we check in terms of the law of constant composition, what we're saying is that if A is part of the reactants, it must also be a component of the products as well. The same applies to B. If it's part of the reactants, it must be part of the products. Then the law of conservation of mass becomes very, very important in the sense that what it says is that for whatever we put in as reactants in terms of mass or in terms of the number of atoms, it should be exactly the same or equal to the mass or the number of atoms of the products. That's what we're saying. So you can't, for argument's sake, have, let's say, 50 grams of total mass of reactants, and then we form 100 grams of the product. It simply, law says to us, if something is conserved, it means in terms of mass or the number of atoms, the reactants must equal the products. That's what the law says. But remember, again, we shall use a lot of chemical symbols and chemical formula as far as the periodic table of elements. Just to draw your attention to that, as you recall, we dealt with the periodic table in grade 10, first term. Now, this is what we refer to as the atomic number. So this is the number of, the protons and neutrons. We refer to it as the mass number. But in this case, we talk about the relative, relative atomic mass, relative atomic mass. So the number there at the bottom, according to this periodic table, is the one that represents relative atomic mass, say, of copper. If you look at sodium, it will be 23, magnesium, it will be 24. Those are the numbers that we talk about. So as far as the conservation of mass or atoms, we're not necessarily referring to the atomic number, which we refer to as the proton number. So it becomes very important for us to distinguish between those two. So the chemical equations, in essence, will be used to represent these chemical change, whereby we start with the reactants and we end up having the product. So the product, we want to think of the product as being the new substances that are formed for that reason. Right, okay. Now, I want us to look at the key concepts for today, the law of constant composition. Right, it says a specific chemical compound always consists of the same element in exactly the same ratio and same of whole numbers. In other words, if you look at carbon dioxide, we want to think of carbon dioxide as a molecule. Why is it so? Because carbon dioxide, between the molecule atoms of carbon and oxygen, there are covalent bonds. So this is a molecular substance, which is a gas. So in this case, what we're saying is that there is one mole of carbon, there is one atom of carbon to 2 atoms of oxygen per molecule. Now, this is a molecule which consists of these individual atoms that in this fixed ratio, and it should be a whole number, something that we've also referred to as integers in our maths. So this integer number, which is in the ratio, in other words, it says to us 1 atom of carbon combines with 2 atoms of oxygen in that order. But also, it does not matter what the phase of the substance is, whether the substance is a gas or it's a solid or it's a liquid, the ratio is a whole number of atoms of each of those elements that make up the molecule. In this case, it could be your carbon dioxide, as we have suggested in our example. Right. And again, if you look at ammonia, the molecule of ammonia, it's a molecule, of course, ammonia, because remember, we spoke of the nitrogen ion atom being covalently bonded to 3 atoms of hydrogen in that order. So these are covalent bonds between the atoms of nitrogen and hydrogen. As a result of that, we have this structure or a covalent molecular substance in the ratio of 1:3 in terms of nitrogen to hydrogen. So as you can see, the 1 is a whole number as well as 3. So each molecule will consist of a whole number, a ratio which is in whole numbers. We can look at more typical examples like dinitrogen tetroxide. Di meaning that there are 2 atoms of nitrogen for every 4 atoms of oxygen in this case. You realize again the ratio is also in integers or whole numbers. Now, so it means there are 2 atoms of nitrogen for every 4 atoms of oxygen in every molecule. It means one molecule. I think it's very important for us to understand that at molecular level, when we talk of this molecule of dinitrogen tetroxide, a single unit, or we can think of it as a particle general, consists of 2 atoms of nitrogen for every 4 atoms of oxygens that are covalently bonded. Hence, we shall continue to refer to it as a molecule. Right. Then the law of multiple proportions. The word multiple means many. We can think of proportions as ratios, many ratios. Right. So we say here, if the 2 elements form more than one compound, if it's more than one compound, it certainly means that these 2 or more compounds, they consist of the same atoms. However, what changes is the ratio of the elements that make up that element in the different compounds under consideration. Now, in this case, it also goes back again to the whole numbers. We cannot divorce the law of multiple proportions according to John Dalton, which is what he put forward when we looked at the atomic theory or the atomic model in the first term. We spoke about John Dalton, who came up with all these laws of multiple proportion, as well as the law of the first one that we looked at, which is the law of constant composition. Right. So now it's still the whole numbers. What we're saying is that let's look at compounds, 2 compounds that consist of the same elements per molecule. Now you realize that the ratio in which can differ. As long as the ratio changes, it's no longer the same compound. Take, for example, water, which consists of 2 hydrogen atoms and 1 oxygen atom. This is the proportion in which these atoms of these elements combined. So that is hydrogen and that is oxygen. So our ratio is 2:1. This is in water. Okay, this is the everyday substance that we use. Now, we talk about the peroxide now. But in the peroxide, it still consists of the same individual elements, which is hydrogen and oxygen. However, what has changed in this case is your ratio, which is 2:2. Now, this is multiple proportion because this is the peroxide. You'd think of the peroxide as this chemical substance that we use for the hair dye, all these colors, ginger, green. The peroxide, those are some of the everyday life uses. However, what is important at this point in time is that the ratio in which, or the proportion in which hydrogen and oxygen bond in these individual molecules are different. Hence, we say it's multiple proportions. But we also maintain the fact that these ratios are for whole numbers only, which is very, very important. We have spoken about the carbon dioxide, which is, in this case, carbon to oxygen. The ratio of carbon is to oxygen, which is for carbon dioxide, it's 1:2, right? Yet for the monoxide, it's 1:1. But what is also important is that we realize the fact that the numbers are whole numbers, in this case 1 and 2, which is in the carbon dioxide, and also 1:1, which is very important. So the law of multiple proportions suggests that if two elements form a compound, however, these compounds, there are options or alternatives in terms of the difference in the proportions of the ratio, then that's where the law of multiple proportions comes in. But also very important to emphasize that these ratios must be in whole numbers. Very, very key. Right. Now, we spoke about the law of conservation of mass. Right. Mass, you can think of mass as the amount of matter or particles that make up a material or a substance. Now, the law in its simplest form, it's stated as shown in the cloud that I've just put there, the total mass of particles. Remember, particles are those liquid substances at microscopic level that make up a substance. For a reaction, in reaction, we're talking about a chemical change. We used the hypothetical reaction like A plus B to give us AB, for example, right, in simplest form. Now, what we're saying is that for whatever mass of A and B, these will be our reactants on the left-hand side, right? Because this represents a chemical change, right? And AB will be our product, which is the new substance that has been formed from these individual reactants. You'd want to think of this as a typical synthesis reaction, for example. Not that it doesn't happen even with a dissociation reaction or the one that involves the breakdown. Now, in this case, if you look at the amount of A, or the number of atoms of A, is the same in the reactants as well as in the product. So it's 1 there, and in B, 1. So the total mass on the left-hand side in this case will be, for example, 2, okay? And then if these had the same mass, and on the products again, it will also 2. However, the law draws our attention to the fact that in any chemical change, so the reaction is a chemical change, right? The reaction is a chemical change. Very important to note that, okay, in which the new substances or the products will be formed. So the total in a reaction, the total mass of the particles after the reaction remain constant. If something remains constant, it has been conserved. It means then it doesn't change. So what is going to remain constant is the mass, conserved. So if the mass does not change, then we say it is conserved. So in place of remaining constant, we can say the total mass of particles during a chemical change or in a chemical reaction does not change. So during a chemical change, a reaction or a physical change, the sum, so I've talked about the sum. In this case, the sum is the plus there. Okay, we shall use a typical example to highlight what we mean exactly by the sum, because as far as the hypothetical, we just get a sense of the number of atoms, because we don't take account into account the masses. So in this case, atoms in the reactants must equal atoms in the products. That's in this case, if we had that A plus B, if I can just must give us, let's say, AB. That's the sense that we're talking about. So the number of atoms in the reactants must be the number of atoms in the product. Hence, the total mass must equal before and after a chemical change has taken place. It's very important for us to also note that, because we've spoken about molecules. So if you talk of molecules, we're talking about these covalently bonded, it could be molecules of elements or molecules of compounds. The molecules do not necessarily remain constant. What remains constant is the number of atoms as well as the mass. However, molecules may not be necessarily constant, as we shall establish as we look at the typical examples. Right, having briefly spoke about the law of conservation of mass, I think it's time for us to take a short breather. Then we shall look at the typical examples of how exactly this law of conservation of mass is very relevant as far as chemical changes are concerned. We shall take a short break for now and join us after the short break. All right, guys, welcome after the short break. We've briefly spoken about the law of conservation of mass. Now it's the time for us to delve a little bit deeper into detail by looking at a practical example of how this very important law in chemical reactions plays a key role. Right, so sulfur dioxide, which is SO2, is indicated in the reaction, reacts with oxygen, that's O2. Remember, oxygen is what we refer to as a diatomic molecule of an element. Yet, sulfur dioxide is a molecule of a compound. Very, very important for us to take note of that. That's a compound and that's an element. So molecules do not necessarily refer to compounds alone. So they form sulfur trioxide. Sulfur trioxide, right, as shown in the equation below. Now the question says, use the relative atomic masses on the periodic table to show that the mass is conserved or it remains constant. Right, very, very important to refer to the periodic table because the periodic table is the one that gives us a guide as far as the indication of the relative atomic mass of each and every element, right? So if we've got a compound, we shall consider the individual elements that make up that particular compound. Then if it's oxygen as a diatomic, would refer to the mass. In this case, because it's diatomic, we shall multiply it by 2. Let's go directly to the periodic table and check the masses. Right, now the first element that we have is sulfur. Okay, we look for sulfur. There is our sulfur from the periodic table. The relative atomic mass of sulfur is 32 grams. Okay, this grams per mole, or 32 atomic mass units. We can think of it atomic mass unit. Okay, atomic mass unit. Okay, right, as we discussed it in the first term. And also the other element is also oxygen, which is also 16. So the relative atomic mass of oxygen, each atom of oxygen is 16 atomic mass units. Right, so what we're going to do, we know that our products, according to the law of constant composition, our products will contain the very same elements, however, in different combinations as you have established. Right, so if we can quickly go back to the problem, just a moment. Okay. If we can go back to the question, right, there we are. Now, what we're saying is that we want to use the relative atomic mass. We know that the mass of sulfur is what? Is 32, right? So if sulfur is 32, just to confirm that, sulfur is 32. Yes, sulfur is 32, oxygen is 16. Very important, meaning that without the periodic table, we are not in a position to carry out these calculations. Now, we've got 32 for sulfur, okay, plus 16 for oxygen. But for oxygen, there are 2 atoms because the ratio is 1:2. Right, whatever we're going to get, remember, there are 2 molecules of sulfur dioxide. So a molecule of sulfur dioxide contains 1 sulfur and 2 oxygen atoms. So whatever we get, we shall multiply by 2. So this is what we have as far as sulfur dioxide is concerned. So this is the reactants, plus that of oxygen. Oxygen is 16. But how many atoms of oxygen do we have in this molecule of this element? Is 2. Right. Now, we're going to equate that to the products. So in the products, we've got two molecules, right? Two particulars there is 2 multiplied by the 1 for sulfur, which we say it is 32, plus, because we are adding, which is the sum, plus 16. But how many oxygen atoms are present in a molecule of sulfur trioxide? There are 3 of them, right? So it's very important for us. So, but this equation has already been balanced in terms of the number of molecules on the left as well as on the right. So if you check even the individual atoms that we have, there are 2 sulfur atoms. In this case, the 2 sulfur atoms on the left, 2 sulfur, okay? And then on the right, there's 2 sulfur, which is fine. Right, so sulfur, the number of atoms on the left is the same as the number of atoms on the right for sulfur. If you look at oxygen, we've got 2 times 4 atoms plus 2 atoms, which gives us for oxygen, which means 2 times 2 is 4, plus 2 is 6 atoms. So for oxygen, there's 6 on the left, yet for oxygen on the right, there's 2 times 3, which is 6 as well. Right, 6 for oxygen. So in terms of the number of atoms on the left is equal to number of atoms on the right for each of the 2 elements that make up the reactants as well as the products. Right, now we go to our calculator, all right, just to confirm in terms of the masses. We shall work out as far as the sulfur dioxide and then the oxygen, get the total. So now we've got 2, okay, into, right, 32, which is for sulfur dioxide, plus 16, okay, 16 times 2, right, and then I close the bracket there, okay, plus the one for oxygen, which is 16 times 2, okay, the other reactant, plus 16, okay, times 2, right. What do we get? We get 160 atomic units on the left, right. So let's go to the right and check with the products. Now we've got, let's clear that. It's 2, because there are 2 molecules there of sulfur trioxide in terms of balancing the number of atoms on the left as well as on the right. So 2 multiplied by, open brackets, 32, right, plus 16 times 3. We close the bracket. Okay, 16 times 3. So what do we get? This is equals to 160 atomic mass units. So as you can see now, the mass is conserved, also the number of atoms on the left. So the mass of reactants, in this case, mass of reactants is equals to mass of products. Very important. In this case, it means this chemical change has obeyed the law of conservation of mass. Very, very important. Now, what is very important is also to refer to the periodic table. All the calculations are based on the masses of the individual elements that are involved in the chemical change that we get from the periodic table. So, in other words, we want to recognize that the periodic table is a very useful tool in terms of the law of conservation of mass. Right, let's move forward. And look at the other concepts. Right. Okay, so that was our periodic table. We'll pass it. Right, now we want to see in terms of balancing, writing balancing chemical equations. Remember, for us to arrive at the balancing of equations, we need to understand the word equations first, which is very, very important. From the word equation, we're then going to use the chemical symbols, which we get from the periodic table, and understand whatever reactants get involved in a chemical change, what are the products, then we can transform that into the scientific language, which is the chemical symbol. As I suggested, that the periodic table becomes very, very key. So first things first, the correct formula is very, very important for both the reactants and the products. Okay, we shall separate these using an arrow. Right, some elements are found as molecules. Remember, we spoke about molecules of elements as well as molecules of compounds. Very, very key. Now, we need to be in a position to distinguish between those, right? For example, phosphorus is a molecule which consists of 4 atoms of the same kind, chemically joined. Oxygen, which has got, we call this ozone, 3 atoms of oxygen, chemically bonded. Then we've got diatomic elements, such as hydrogen. This means that atoms of the same kind are chemically joined together by way of covalent bonds to form that atom molecule of an element, which is very, very key. But if you can see, these are atoms of the same kind. Now, hence, these are elements for that reason. Very, very key. So for us to understand the chemical formula becomes very, very important. If it's ionic, let's say sodium, sodium, let's say maybe magnesium, or let's say sodium, which is I plus, okay, it forms a cation, and let's say iodine minus, when it reacts to form an ionic compound. This has to do with ions, right? So ionic compounds, so that's our cation, and then anion, we have got NaI. So sodium iodide gets that formula because the total charge, the net charge is 0 for the reactants, and the net charge for the product is also 0. What also becomes very important is to indicate the phase in which the substance occurs. At room temperature, or let's take for example oxygen. We know oxygen is a gas at room temperature. We know that water exists as a liquid at room temperature. So this is very, very important. So these three phases are also important in terms of indicating the phase of the reactant as well as the product. Become very, very, very key. Aqueous solutions, you can think of aqueous solutions, for example, the acids which exist in liquid form. Take, for example, sulfuric acid. It will be H2SO4 aqueous. It means it's dissolved in a solvent or in water to give us that solution. Right, so we have to separate that with an arrow. Remember, we said A plus B, which are our reactants. We separate the reactants from the product using an arrow. Very, very important as well. So now we're going to count the number of atoms on the left. In this case, there's one atom of element A, whatever that is, and then there's also one on the right. There's one of B, one of B on the other side. So the number of atoms must be equal on the left as well as on the right for both the reactants and the products, according to the law of conservation of mass or atoms. We can call it law of conservation of atoms. Very, very important. So if something is conserved, it means it remains constant. Law of conservation of atoms, meaning atoms of products must equal the number of atoms of reactants. Right. So if they're not the same, well, if for whatever reason they're not the same, let's say, for example, we've got A, plus B2, which is a molecule, then it gives us AB, something like that. So what we're going to do, we'll count the number of atoms. There are 2 atoms in this molecule, so we also need to have 2 there. Now, if you check on A, now we've got 2 atoms of A, which means on the reactants we also need to have 2. Now, this is how we do, without necessarily changing the formula of the compound. We only change this. Some in maths would refer to it as the coefficient. Right, so we only change the coefficient as far as balancing the equations of reactions. Right. Okay, right. This is a simple example that we're going to look at. It talks about balancing a chemical reaction. If you can realize the fact that this one is written in words, now we need to also transform this into chemical symbols. Our periodic table becomes very important. We know that sodium is Na, and we know that chlorine is one of those diatomic elements. So it's going to be Cl2. And also sodium, we know it's a solid, and then chlorine, we know it's a gas. So the phases become very important. And again, we know the arrow separates the products from the reactants. So we know that we form sodium chloride, the ions must be balanced. That's 1, 1, which is +1, and -1, so that's 0. But if you look at this, sodium chloride is a solid substance, right? If you look at the number of atoms of sodium, on the left we've got 1, and then on the right we've got 1 number of atoms, right? Yet if you look at chlorine, we've got 2 atoms, and then on the right hand side we've got only 1. So we agreed that we're going to change only the number of molecules. If there are 2 on the left, it means we also need to put a 2 on the right. However, that changes the number of atoms of sodium, which means even on the other end, now that there are 2 on this side, it means the atoms of chlorine are balanced, yet those of sodium are not balanced. We're also going to put the 2 there. So in terms of balancing, it's very important for us to count the individual number of atoms, and then we only change the coefficient, which is the number before the chemical formula, not necessarily changing the formula of the substance or the chemical formula of that particular reactant or a product. Very, very important. Right. Okay. Now, this is the periodic table. You know, we transformed the words into symbol. That's our sodium. There is our chlorine. So our product must consist of these two elements. Very, very important. Right. Now, I'll give you a minute to try and attempt the question based on the balancing. Having done a brief an example and explained in detail as to the steps or the logic in terms of trying to balance an equation. Write down the balance equation for aluminium, which reacts with hydrogen chloride. And then after the short break, what we'll do, we'll start immediately with our feedback. So I'll give you a minute for that. Then we'll do the consolidation of this balancing of equation. All the best, guys. Let's go for it. Right, let's go back to the feedback of the question that I just gave to you, which has to do with the balancing. And remember the chemical symbols as well as the phases in which the substances, be it the products or the reactants exist. We also need to indicate that as well in our chemical equation. Right, so aluminium, we know that aluminium is a solid, you know, it exists as a solid. So it will be aluminium, which is solid, right, plus the hydrogen chloride, but this is a solution. You know, if it's a solution, we know it's AQ, which is aqueous. So HCl aqueous. Sometimes we refer to this solution as hydrochloric acid. So this is a metal which reacts with an acid to form a solution of aluminium chloride. Right. Now, if we go to aluminium chloride, in the first term we looked at the common cations and the common anions. You'd recall that aluminium is Al3+. This is the most common aluminium ion. And we know chlorine, because of its valency of 1, it's going to be a Cl-. So our product that will be formed would be AlCl3, right? This is an aqueous solution, okay? An aqueous solution which reacts with plus, which also has another byproduct, which is hydrogen gas. And remember, hydrogen is a what you call a diatomic element. So it's a molecule of an element. So if you count the number of atoms of each element, you'd realize that there's one for aluminium, okay, and one for aluminium, which is still fine, okay? Then if we go to the chlorine, we've got one for chlorine, and then again 3 for chlorine, right? It gives us a little bit of a problem. Now, if you check, hydrogen is 2 and hydrogen is 1 in this case. It's very important for us to count, because when we count, we can then only be in a position to say, okay, now if we say, for argument's sake, let me rewrite this equation clearly so that we have enough space. So it's Al solid plus HCl aqueous, which is a solution, to give us Al, so I'm writing it in using chemical formula, Cl3, aluminum chloride plus hydrogen gas, right? Okay, so if we have hydrogen gas there, it simply means that we can think of it this way, right? I'll use a different color, for example, right? And say, okay, if there's 2 of hydrogen there and 1 of hydrogen, and then there's 3 of chlorine, and there's 1 of chlorine. Surely something needs to be done. If we say, okay, for argument's sake, the number which is common between 2 and 3, the lowest common multiple, if I put a 6 there, I would have 6 hydrogen, you know, and then 2 2 hydrogen to give us 6, I need to add 3 there because to give us 6, right? However, chlorine already has 3, but on the other side it has 6, which means I'll have 2 moles there, or 2 molecules of this product. But if you look at aluminium, in this case, we've got 2 aluminium, 1 on the right. It means we also need a 2. So if we're going to count the number of atoms, so the elements that we have, so we've got aluminium, we've got hydrogen, we've got chlorine. So we've got reactants, okay? We've got also the products, right? So we're going to check for if it's balanced, right? And then, okay, then we have the hydrogen there. Can I just rewrite that? Okay. Okay, because this is Al, and then that's our hydrogen. So on the reactants, we've got 2 atoms of aluminium. On the products, we have 2, so aluminium is balanced, okay, in terms of the number of atoms of the element in the reactants as well as in the product. If we go further, we've got, for hydrogen, we've got 6 on the left, which is the reactants. We also have 6 on the right, which is the product. If we go to chlorine, it's also 6, 6. So indeed, the equation is balanced by merely counting the number of atoms, which merely translates to the fact that even if we had to consider the relative atomic masses after adding the 2s and the 3s in terms of the molecules, it would work out to the same thing as long as the individual number of atoms is the same. Right, having done that, hopefully that makes a lot of sense to us. Can we then, for now, take a short breather, then we join after the break to do the remainder of the session. See you after the break. All right, guys, welcome back from a short ad break. Let's look at the other questions that has to do with the balancing of equation, counting the number of atoms. We may also refer to the periodic table and apply the law of conservation of mass, which is pretty much the same as the law of conservation of atoms in a chemical change. Now, this one says nitrogen gas, take note of that, reacts with hydrogen gas to form nitrogen trihydride gas, which we refer to as ammonia. So write down a balanced equation for the reaction, right? I'll give you 2 minutes for that, and then we'll do the feedback. Let's go for it, guys. Okay, guys, hopefully you've made your attempt on the question of balancing the equation between nitrogen gas as well as hydrogen. But it's very important for us. We may refer to the periodic table just to identify the elements. It's our hydrogen as well as our nitrogen. So our reactants consist of these two elements. However, it's important for us to also recall that nitrogen gas is diatomic. It's a molecule of an element which consists of two atoms that are chemically joined together. However, also it's a gas, which is the phase at which it exists. Very, very key. It reacts with hydrogen, another diatomic molecule of an element. Right. So that's another gas, okay, to form ammonia, which is nitrogen trihydride. So it means the ratio of nitrogen to hydrogen in the products is a 1:3, which is our new substance that has been formed in this chemical change. Right. Now we're going to consider the number of atoms on the left and the number of atoms on the right. So if you look at nitrogen is 2, then if it's 2 there, it simply means that we have 1 for nitrogen. It's not balanced. And then also for hydrogen, it's 3 on the left and then 2 on the right. Okay, maybe we may consider starting with hydrogen. So the lowest common multiple in this case, the number that can balance 2 and 3, is that if we multiply by 3 on the left and we multiply by 2 on the right, I think it kind of gives us an idea that the elements that we have, so our table, which we can use to confirm. So the element in this case is nitrogen and hydrogen, right? Okay. So this one's for reactants, and the other one is for the products. As far as it stands, we did not change the formula of the substance. We only changed the coefficients, right? So 2 atoms on the left for nitrogen, and 2 atoms on the right for nitrogen. So indeed, nitrogen is balanced. Mass, or the number of atoms, has been conserved. We also look at hydrogen, 6 atoms in total, which comes from 3 multiplied by 2. In this case, it's 6 on the left and 6 on the right. So indeed, the equation of reaction is balanced, right? So it's very important for us to refer to that, right? So these are some of the most common substances. Hydrochloric acid, which is an aqueous solution that we discussed in the previous example, and also nitric acid, which is an aqueous solution. This is sulfurous acid, the one that comes from sulfur dioxide and water in the rain, which is called, sometimes we call it the acid rain, the one that corrodes buildings. So also this one is an aqueous solution, and also sulfuric acid, which is an aqueous solution, right? Now, so these are some of the common substances that we use. Now, I'll give you exactly 4 minutes to try and attempt these equations in terms of balancing. Then we'll do the feedback. Right, 3 minutes will do for that. The reaction which are given in words, we need to transform this into chemical symbols. Right, let's go for it for 3 minutes. Then we do the feedback and the consolidation. Right. Welcome back, guys. Hopefully you've made your attempt on the 4 questions that involve the balancing. Right, let's get right on to the feedback. Right, so the periodic table becomes very important in identifying the elements. Right, we know that aluminium is Al from the periodic table, which exists in solid, and the oxygen, which is a diatomic molecule of an element, to give us aluminium oxide. As far as aluminium oxide, we know that it's Al3 plus and then O2 minus. Right, so our formula, it means to balance the number of ions, it means so that the net charge on the left equals net charge on the right, we've got Al2O3, right? So where this is a solid, right? Now, if you check, aluminium is 2 on the left and on the right and 1 on the left. So oxygen is 3 and 2. So we might consider starting with the oxygen because the number that can balance this, it means if we say, okay, we have 2 here, it means oxygen will now be 6, right? And then if we can have 3 for oxygen on the left, right, it means now just to use a different color, so that we identify the molecules. Right, so it means oxygen is balanced, and then aluminium, there's 4 in this case, yet on the other side is 1, it means then we put the 4 there. So indeed, our equation is balanced. Sulfur dioxide, 1:2 for sulfur to oxygen, reacting with, this is a gas, plus water, which is a common one, it's liquid. We can think of this as the rain. It reacts to form sulfurous acid, which is the acid rain, H2SO3, which is aqueous, it's a solution. So sulfur dioxide dissolves in water to give us that. If you look at, for example, the hydrogen is 2,2, but the oxygen is 3 this side, right? If oxygen is 3, it means then we've got 3 on the left for oxygen, right? And 3 on the right. Sulfur is 1:1, oxygen, hydrogen 1:1. The 2:2, meaning that sulfur is 1, here it's 1. Oxygen in this case is 3, oxygen is 3 on the left hand side. Hydrogen is 2 on the right, and also hydrogen is 2. So already the equation of reaction is balanced. We need not tamper with it. Right, very important. And then we also have zinc, right? Zinc, which is a metal, Zn, reacts with HCl. This is a solid which reacts with hydrochloric acid, metal plus, from Gr9, we know that a metal reacts with an acid to give us a salt, which is zinc chloride. Chloride is 2 there, which is that plus hydrogen gas, right? Okay, very key. Then we also understand that the zinc is balanced, the chlorine are not balanced, and if you check, there's 2 atoms of hydrogen on the right, and there's 1. So if we balance that, it also takes care of the chlorine, which also has 2. Very, very important. Right. So according to this reaction, this is the balanced equation of reaction. Right. Okay. Now the last equation is between aluminium, okay, which reacts with sulfuric acid, which is H2SO4, which is an aqueous solution. Right. Aluminium is a solid. To give us aluminium sulfate. Aluminium sulfate is Al2SO4. Aluminium is 3 plus, sulfate is 2 minus, so it's SO4 3. That's aluminium sulfate, okay, plus hydrogen gas. All right, this is a gas, and this in sulfate is an aqueous solution. Right, then we need to check the individual number of atoms. It's 2 aluminium, okay, 1 on the left, there's 2 hydrogen there, so it's 2 hydrogen. So if we can put the 2 there for aluminium, and if you check sulfur is, in this case, we've got 3 sulfur. In this case, sulfur is 2, we've got 1 sulfur. This side is 3, right? So that about changes everything. We also need to be very careful in terms of counting the number of atoms. So that's also another key aspect. So without any waste of time, due to time constraints, I would want you to try balancing by way of counting the number of individual atoms on the left and on the right for each and every element. Right, due to the time constraints, I think we shall leave that as part of a extended activity that that you can do it on your own, and maybe try to check with your friends. And then this has brought us to the end of our session today, which we looked at the law of constant composition, the law of conservation of mass representing chemical change as far as the law of conservation of mass is concerned. Right. Hopefully you had a splendid session for the day. I hope to see you next time at the same segment. Cheers and bye-bye for now.